Frito-Lay Corporation's Jeff Swearingen said, "Sometimes a great shopper insight is more valuable than a great product." In this lesson, we're going to compute combinations. We're going to compute unbiased estimators. We're going to determine if a statistic is biased or unbiased. And we're going to critique sampling techniques. All to answer the question, how can corporations use small groups to make inferences about public's spending habits? Before we get into it, let's take a look at warm-up number 2. Find the slope of each of the straight lines with the following equations. Well, in the first one, it is in y is mx plus b, meaning 4 is the slope. In the second one, while it's written backwards, it is still in y is mx plus b form, and 5 is the slope. Now on C, we need to divide everything by 2, giving us y is 3x minus 7, and 3 is the slope. Now let's take a look at a problem you will be able to do by the end of this lesson. The following shows the number of skateboards sold for the first 4 weeks of November at Skateland Athletics. The trend shows sales seem to be declining. If samples of size 2 were taken with replacement, how much do the sample means cluster around the real population mean? You're going to use this data to uncover a very important property of sample means. First, set up all possible samples of size 2 taken with replacement. It might be helpful to build a table to organize your data and a simple mean. Notice you pick 1 week to be the representative of a typical November week sales. None of the individual weeks would represent the population mean of 4.5 very well. None of the numbers are even as close as 1 unit to 4.5. However, notice that 8 of the 16 samples had a mean in the interval of 3.5 to 5.5, and these are very close to the population mean. 50% of the sample means cluster around the population mean. It is reassuring to know how much the sample mean cluster around the population mean because it tells us the single sample we pick had a good chance of approximating the population mean well. Before a corporation can allocate the money to mass produce new inventions, they must make sure the public will buy their new product. Certainly they can't give millions of people a survey. That would be too costly, time-consuming, and take an incredible amount of effort. Have you ever read in an article online or in a newspaper about the public's spending habits? Did you ever wonder, how can they talk about everybody's spending habits? They never asked me to participate in this survey. How can a corporation reliably find out if there is a market for their new product? How can manufacturers and stores put trust in these surveys since they do not include everybody? The answer to these questions require us to define some new terms. The specific groups you're looking to study are called a population. You may be interested in the opinions of a population of teenage boys or senior citizens. A population does not have to be made up of people. You may be studying a population of cell phones, coffee cups, pens, or gas stations. You could be interested in the population of all tennis rackets manufactured by a certain company. Any subset of the population is called a sample. Studying a sample is more feasible than studying the entire population because entire populations are sometimes large and or impossible to access. Manufacturers often employ a focus group, a sample of a population they use to evaluate a product. There are many different ways to choose a sample. Carefully sampling is a cornerstone of good statistics. Often, market researchers are looking to generalize about populations that are very large. In that case, they can take a sample and make a generalization about the entire population. This field is called inferential statistics. The next time you see a commercial for a new product, you can be sure the corporation used sampling and inferential statistics, which you learn in this section before manufacturing their new product. You know how to compute measures of central tendency, dispersion, and regression. However, these computations should be made on a sample data that has a good chance of being representative of the entire population. If a corporate executive wanted an opinion on a new product, would he just use his family or bowling team as a sample? Of course, that would be convenient because he had access to these samples. For this reason, this type of sample is called a convenient sample. A convenient sample is a sample that is easily accessible to the researcher. If you were doing a study, your class, sports team, neighborhood, or community center would be considered convenient samples for you. There are potential disadvantages to using convenient samples. They often may not be a representative cross-section of your population. Samples can be taken with or without replacement. Without replacement, once a subject is picked for a sample, it may not be picked again for the sample. With replacement, once a subject is picked, it may be picked again for the sample. Although many mathematical methods are based on sampling with replacement, in actuality, sampling is often done without replacement. Samples are created without regard to order are called combinations. When you select a subject for a sample, it does not matter what order the subjects are selected in. The combination of Mary, Joe, and Ellen is a combination of Joe, Mary, and Ellen. To determine the number of possible different combinations of Joe, Mary, and Ellen, or anything else, you need to learn about factorials, which are indicated by an exclamation point in mathematics. The factorial of a positive integer is the product of the integer and every positive integer less than it. An ellipsis, 3 periods, indicating missing numbers, is the indicating series of factors. Look at these examples. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equal to 120. 13 factorial is equal to 13 times 12 times 11, and so on, times 3 times 2 and times 1, to equal 6,227,020,800. When dividing factorials, you can expand them and reach common factors which can be canceled out. Like 10 factorial divided by 7 factorial is equal to 10 times 9 times 8 times 7 factorial, all divided by 7 factorial, which will leave us with 10 times 9 times 8, which is 720. Now let's compute combinations. A common method of sampling that aims to reduce the bias is to take a simple random sample. A sample is a simple random sample if it has the same chance of being selected as every other sample with the same sample size. Let's say you want to take samples of size R from a population size N. If you are taking a sample randomly, then every different possible set of size R has the same chance of being selected to be in the survey. How many different samples of size 6 can be taken from a class of 28 students without replacement? You are looking for a different number of combinations of 6 that you can take from a group of 28. You can use the combination formulas. Factorials will be used in the combination formula. We're going to let N represent the population, which is 28 students. And we're going to let R represent the size of the sample, which is 6 students. The notation to represent the number of combination is NCR. Now, this is going to be equal to N factorial divided by R factorial times N minus R factorial. So if we go ahead and substitute, what we get is 28C6. And to find that, we're going to do 28 factorial divided by 6 factorial, 28 minus 6 factorial. This is going to give us 28 factorial divided by 6 factorial times 22 factorial. This means we're going to have 28 times 27 times 26 times 25 times 24 times 23 divided by 6 times 5 times 4 times 3 times 2 times 1. And this is going to give us 376,740. So in a class of 28 students, over 300,000 different samples of 6 students can be formed. Look for that NCR command on your calculator and learn how to use it. On a TI-30XA, we can see the NCR is located above the 8. What we're going to do is 28 second, hit the NCR 6, and hit equals. And we can get the 376,740. Let's check our understanding. A store looking to increase business on weekdays is randomly picking 4 customers every Wednesday to go on a free shopping spree as a promotional event. If 192 people shop on a certain Wednesday, how many different groups of 4 can win the prize? So we're looking at 192 C4. This would be equal to 192 factorial divided by 4 factorial times 192 minus 4 factorial. Now we can do this on our calculator by doing 192 second NCR 4 equals. And that's going to give us 54870,480, and go add those commas. The Lockstep Corporation manufactures different types of locks. They need to do quality control analysis, and they need a sample of locks they manufacture. Rather than take a simple random sample, they want a sample to have the same percentage breakdown as the type of locks they produce. This is called a stratified random sample. The following table gives the percentage breakdown of locks they manufacture. If their sample is to contain 800 locks, how many combination locks should be selected for the sample? The sample is supposed to be proportional to the same as the population of locks they produce. Since 15% of the locks are manufactured are combination locks, they need to find 15% of 800. That means they're going to take the 800 locks and multiply it by 0.15 to get 120. So the sample of 800 locks should have 120 combination locks. Let's check our understanding. Use the data from example 2. How many more keyed locks will the sample have compared to digital coded locks? Well, we know the sample size is 800. And of that, 50% of them are keyed lock. So that is 0.5, or 400 keyed locks. The sample size is still 800, and digital locks represent 5%, which is 40 locks. So subtracting them, we get there is 360 more keyed locks than digital locks. Let's extend our understanding of this. If Lockstep took a simple random sample instead of a stratified random sample, is it possible their sample could have been composed of only keyed locks? In short and easy, yes, it's completely possible. Now let's determine if a statistic is biased or unbiased. Beth's Bagels is trying to find out how its customers feel about having colored bagels that use food dyes to celebrate certain holidays. They send 100 emails to randomly selected town residents. Explain the disadvantages of this method of sampling. This sample has a severe problem. It is called undercoverage. Undercoverage occurs when a part of the population does not have a chance to be in the sample. In this example, anyone who has not provided an email to the town could not be selected for the sample. This left out part of the population: people who are privacy conscious, people who are not computer savvy, or people who cannot afford technology. Let's check your understanding. A calculator company wants input from math students. They take a random sample of students from 5th period math class in a local high school to give them a questionnaire. Explain why this is an example of undercoverage. Students who do not have math 5th period have no chance of being in the sample. Now let's critique sampling technique. A drug company is doing a study on obesity to see if a drug they are developing actually works. They randomly select 100 people and have them fill out a questionnaire on their weight, diet, and exercise habits. Explain a possible disadvantage of this sampling scenario. When information of a personal nature is involved, people might not answer honestly. This is called non-response. If you don't comply with the requirements of the study, you are guilty of non-response. If study requires you to perform a task, example, exercise 20 minutes a day, and you don't comply, you are guilty of non-response. If you don't answer the questionnaire at all, you are guilty of a form of non-response called self-selection. Let's check our understanding. Explain why a questionnaire asking adults about their income could be the subject to non-response. People are self-conscious about the amount of money that they make. Let's compute unbiased estimators. Nature's Way is a health food company looking to open new restaurants. The following shows the number of organic food restaurants in a small city for each of the past 6 years. To illustrate the power of sampling, we view these 6 numbers as a population of 6. Sampling properly can give a researcher important information. Notice the population mean is 11. There are 6C3 equal to 20 different samples of size 3 taken without replacement. All of the possible samples without replacement are listed here. Find the mean of each sample as a fraction. Once you have completed finding the mean of each sample as a fraction, find the mean of all sample means. For each sample, add the number and divide by 3 and express your answer as an improper fraction, which you can see here on the screen. The mean of the 20 sample means is also 11, the same as the population mean. For this reason, the sample mean is called an unbiased estimator of the population mean, when the mean of statistics taken from all possible with replacement is equal to the actual population mean. Note that this also occurs in the example when the samples are taken without replacement. Let's check your understanding. A used car dealer sold this many cars for each of the past 5 weeks, Monday through Friday. Take all samples of size 2 without replacement. Find the mean of each sample and the mean of all sample means. Based on this, do you think the mean is an unbiased estimator? The mean of the data is 6, and the mean of the 10 different possible samples is 6. Based on this, the mean seems to be an unbiased estimator. Let's extend our understanding a little bit. Determine the sample median is an unbiased estimator of the population median by using the data from example 4 and explain your reasoning. The median of the data is 6, and the mean of 10 sample means is also 6. Based on this, the mean seems to be an unbiased estimator. The data from example 5 shows a trend that organic restaurants are becoming more popular. Look at the data and find the range of each sample. Determine if the sample range is unbiased estimator of the population range. The population range is 22. The sample ranges are shown on the table. The mean of the 20 samples range is 16. Since the mean of the sample ranges does not equal the population range, the sample range is not an unbiased estimator. The sample range underestimates the population range because most of the samples do not have the extreme scores in them. It is not a good idea to use range taken from samples to approximate the population's range. Let's check your understanding. Use a hypothetical population of 5 scores below and take the sample size of 2 without replacement. Find the population range and mean of the 10 sample ranges and show they're not equivalent. The mean of the sample range is 3.2 and the population range is 6. The following shows the number of skateboards sold for the first 4 weeks of November at Skateland Athletics. The trend shows sales seem to be declining. If samples of size 2 are taken with replacement, how much do the sample means cluster around the real population mean? You're going to use this data to uncover a very important property of sample means. First, set up all possible samples of size 2 taken with replacement. It might be helpful to build a table to organize your data and a simple mean. Notice you pick 1 week to be the representative of a typical November week sales. None of the individual weeks would represent the population mean of 4.5 very well. None of the numbers are even as close as 1 unit to 4.5. However, notice that 8 of the 16 samples had a mean in the interval of 3.5 to 5.5, and these are very close to the population mean. 50% of the sample means cluster around the population mean. It is reassuring to know how much the sample mean cluster around the population mean because it tells us the single sample we picked had a good chance of approximating the population mean well. Let's check our understanding. For dataset 2451, the sample size of 2 taken with replacement, how many samples have a mean that are 1 unit or less away from the population mean? 10 of the possible 16 samples taken with replacement have means within 1 unit of the population mean of 3.